Okay, any questions? Any questions about anything? Let me just write down when this lecture ends. Okay. So, questions? Questions? Jade. Funny that you should ask that question. It's probably like 12 weeks-ish now, which is like twice as long. Question was, when was the last time I got a haircut? I think it was like 12 weeks ago. I think it was in January sometime, and usually I go like 6 weeks, so yeah, it's getting a little bit out of control. But Carrie? Oh, her name is Stella. Who cuts my hair? Her name is Stella. And she used to have a salon over at Collegetown, but then she moved out to her house up the lake in Interlaken, and then she and her husband, when their kid went to college, they moved to a small apartment, so she couldn't do it there anymore. And now she comes and cuts your hair in your own house. So I have a hairstylist who makes house calls, but unfortunately she's not allowed to do that right now because of everything that's going on. So anyway, yeah, I used to have awesome hair back in the 80s. Maybe I'll post a picture, but now it's not as good as it was. And I kind of like the fact that, you know, long hair is back in style for males now, so I look around the room, I see a bunch of examples of people with cool hair. We should probably have a vote, like who has the coolest hair. I don't know, I would say Cameron maybe probably has the coolest hair. Partly because when I look over there and I only see hair, then I know he's on his phone. So anyway, enough about haircuts. So any questions about anything else? Okay, well, remember last time we started talking about these so-called IIR systems. And if I can ever get the chalk open, we can continue talking about them. So, recall we started talking about a new class of systems, and essentially the name of these things are they're generally IIR systems, infinite impulse response. We'll get to that a little later on, but they're governed by the following difference equations. Y of n is equal to the sum from k equals 1 to cap n of ak, y of n minus k, plus the sum from k equals 1 to n of bk, x of n minus k. And by the way, last time I noted that we can always assume that the lengths of these two sums are the same just by having certain coefficients be 0 or whatever, just gets rid of another variable to kick around. And notice that FIR systems, causal FIR systems, and so the assumption here is that the systems are causal. We'll talk more about that. Note that causal this is k equals 0 to n. Boy, I'm getting off to a rough start today. Note that FIR systems are a special case of this kind of system. If we just have all the AKs be 0, then we just have y of n is equal to the sum of a bunch of past x's. So note that. Just in passing, a causal FIR systems are special cases of these. Just set all these recursion terms, the terms involving past y's, ak equal to 0 for k between 1 and cap n. All right, now we have to be careful here. We have to be careful. In what sense does this define an input-output relationship where you have x of n signal going into the system, y of n output signal coming out? To make that work, we have to be careful. Okay, so we need to sort of do some more pinning things down. So we need to pin things down a bit more to get this kind of a difference equation to represent a legitimate input-output relationship, a well-defined relationship that takes input signals to output signals. So to get this to represent a well-defined I/O mapping. X of n goes in, and y of n comes out. How do we do that? How do we pin things down? The way we do that is we restrict for now, and again, later on this is going to get relaxed a little bit. So for now, what we're going to do is, and I want to emphasize this, is going to change when we get deeper into this stuff. For now, what we're going to do is restrict our attention to a specific universe of signals. Okay, so restrict our attention to the, what I'm going to call the universe, quote unquote, universe of signals that are 0 for negative time value, for n less than 0. Okay? And as we go through this, occasionally what I'm going to be saying is such and such is true because of the universe assumption. I think you'll understand what I mean by that as we go along. Okay, now the book has a name for this. The book has a name for this. The book calls this, quote unquote, initial rest conditions. But I'm not going to use that terminology. I'm just going to talk about restricting our whole attention to the universe of signals that are 0 for n less than 0. If we restrict our attention, so in any event, if we restrict our attention to this universe of signals, then it turns out that this equation here gives rise to a well-defined I/O relationship that takes any signal x of n in that universe and gives us a well-defined signal y of n in that universe. So in any event, here's the fact that if within this universe of signals, the difference equation above gives rise to a well-defined I/O mapping. It unambiguously determines the output signal y of n in terms of the input signal x of n. In other words, you give me signal x of n, I can tell you what the signal y of n is. And you may say, well, why doesn't it do that anyway? What's up with this universe thing? Well, if you look at this difference equation, and someone comes up to you in Whole Plaza and says, you know, I want to figure out the response of the system to the signal x of n equals u of n, say, a unit step input. How do I figure that out? Well, you can put u for x, that's fine. But then they say, okay, well, what is y of n? What is y of 0? And you may say, okay, y of 0 has to equal the sum from k equals 1 to n of ak y of 0 minus k plus the sum of the bk's. What are those earlier y's? I don't know, without anything further. So what I really need to do is, in order to have this give me a well-defined x to y mapping, I have to have a way of getting rid of the ambiguity that arises because of the recursion terms. So here's the basic idea. Say we're given x of n. X of n is given and in the universe. Okay, whenever I say universe, I'm always going to mean for now a set of signals from 0 for n less than 0. Let's figure out y of n given that y of n is in the universe. So, since y of n is in the universe, y of n equals what for n less than 0? Mustafa. Yes, 0. Okay. That's what it means to be in the universe. You are 0 for n less than 0. All right. So now all we need to do is figure out y of n for n bigger than or equal to 0. Okay, so what is y of 0? How do we figure that out? We go to the difference equation. So we go to the difference equation, and we get y of 0 equals the sum from k equals 1 to n of ak, y of 0 minus k, which is minus k, plus the sum from k equals 0 to n of bk x of 0 minus k, which is just minus k. All right? The first sum here, aky of minus k, k running from 1 to n. All those are zeros. Why are they zeros? One word answer. Universe. Very good. Who said that? 3 people. Okay, well you can fight it out. Okay, all these terms are 0 by universe. Or because universe. However you want me to say that, I'll say it. That's what I mean. How about these? The bkx of minus k. Well, one of them might be non-zero because k equals 0. X of 0 might have a non-zero value, but all the rest are 0. So all 0 because universe, use both terminologies there, except maybe the k equals 0 term. Conclusion. Y of 0 equals b0x of 0. That's the only term on the whole right-hand side of the difference equation that has a chance to be non-zero because of the universe assumption. All right, so now we know y of 0. All right, cool. How do we figure out y of 1? So y of 1. So next, we want y of 1. Y of 1 equals, again, the sum from k equals 1 to n of ak, y of 1 minus k, plus the sum from k equals 0 to n, bk x of 1 minus k. All right, now we have a term in this one that might be non-zero, which is the k equals 1 term, because you have a y of 0 there that you've already figured out. All the rest are 0. So this is first sum. It's going to be a1 y of 0 plus a bunch of zeros. And over here, now we have 2 terms that are allowed to be non-zero. The ones where k equals 0 and the ones where k equals 1. The one where k equals 1 is b1 x of 0. And the other one is going to, or sorry, yeah. Let me write it this way. Where's the red erase? It's b0 x of 1 plus b1 x of 0. And the rest of the terms are 0 because universe. So y of 1 equals a1 y of 0 plus b0 x1 and so on. We've already figured out what y of 0 is in terms of x. Conclusion that y of 1 is equal to a1 b0 x of 0, that's from this first term, plus b0 x of 1 plus b1 x of 0. All right. Now what? Now we get y of 2. How do we get y of 2? We plug n equals 2 into the difference equation, and on the right-hand side we have terms involving stuff we've already figured out. Past values of y, past and present values of x. Bottom line, so it's obvious how to continue this. To get y of n bigger than or equal to 2. But the moral of the story is, you give me an x in the universe, I give you the y in the universe that arises from the difference equations. So that's the important thing to know. So the important thing is that under the universe assumption, the signal, input signal x of n determines the output signal y of n unambiguously via the difference equation. Okay? Now, clearly, if you want to figure out the output of this system for a given x of n in the universe, you're not going to want to figure it out like one value at a time, go through these kind of manipulations. That's obviously too tedious. There's better ways of doing that, and we'll get to those as we go along. But for now, I just wanted to convince you that under this assumption that we're dealing for now only with signals, there's 0 for n less than 0, that difference equation gives us a well-defined I/O mapping. All right. Okay, so let's look at this system. Let's figure out what happens when I put an impulse into the system. What comes out is something I'm going to call, as usual, the impulse response. So, as usual, we can define the impulse response h of n as the output signal that arises when x of n, the input signal, is a delta function in a discrete time impulse. Now we have to be careful, right? We only have a well-defined I/O mapping when we assume that the input and the output are in the universe. Is delta in the universe? Yes, delta is in the universe. So note delta of n is equal to 0 when n is less than 0. So delta of n is in the universe. So our h of n here is well defined. What is it? Well, I'm going to look at just an example rather than go through it in general. So an example of figuring out h of n, one value at a time. That's easy. Let's do an easy example. So, a simple example. Let's look at the system y of n is equal to, say, a1 y of n minus 1 plus b0 x of n. So that's a specific example of one of those difference equations. You've got only one a term, you've got only one b term. Let's figure out the impulse response. So let's figure out h of n. So first you set x of n equal to delta of n. Okay? And then you figure out y of n. How do you figure out y of n? So h of n is equal to the y of n that arises. First, h of n is equal to 0 when n is less than 0. Why is that the case? Because of the universe assumption. So that's by the universe assumption. And alternatively, it's by the causality of the system, which we assumed. And I want to get back to the causality issue later on. I don't want to dwell on it at this point. Okay, get back to that. How about for n bigger than or equal to 0? Let's figure out the values of h of n one at a time. So for n bigger than or equal to 0, you can compute h of n one value at a time as above. So let's do that. In this simple example, the one value at a time computation is okay. So what's h of 0? H of 0 is equal to a1 h of minus 1 plus b0 delta of 0, because x of n is delta of n. That's what I plug in for the delta function every time when I'm figuring out the impulse response. This is 0. And this guy here is 1. Answer b0. That's what h of 0 is. Everybody see that? All right. How about h of 1? H of 1 equals a1 h of 0, that we've already figured out, plus b0 delta of 1. What's delta of 1? Come on. Amelia. Yes. Delta of 1 is 0. So that term goes away, and I get a1 h of 0, which is b0, so I have b0 times a1. H of 2. And after a couple of these, you can see what's happening. H of 2 is a1 h of 1 plus b0 delta of 2. Again, delta of 2 is 0. a1 h of 1 just multiplies another a1 in there, and I get b0 a1 squared. And similarly, you can show that h of n for an arbitrary n bigger than or equal to 0 is equal to b0 times a1 to the n minus 1, or a1 to the n for all n bigger than or equal to 0. Carrying on. Conclusion. Bottom line. H of n is equal to, let me write it up here so I can do it in the piecewise form we've come to know and love, and then collapse it down a little bit. The bottom line, h of n is equal to 0 when n is less than 0, and it's equal to b0 times a1 to the n when n is bigger than or equal to 0. And what's a slick way of writing that? Anybody? Yes. Unit step. B0, A1 to the n times a unit step. So that's the impulse response of the system governed by that difference equation over there. Causal system governed by that difference equation. Okay, so far so good? On the same page? Jack. Yes, yes, the question is, okay, I keep throwing in the word causal here, causal there. I started off this discussion saying we're going to talk about causal systems governed by difference equations of this form, as if causality is a background assumption of this whole thing. And yes, it is. It is a background assumption of this whole thing. And you can even say h of n is equal to 0 when n is less than 0 by causality of the system, rather than by the universe assumption. Okay, but let me just I think you're right. You're right to raise that question, okay? Because it's a matter that confuses people when we go through this stuff. So let me just mention that just from an aside here. Throughout this discussion, we're assuming, as part of our background assumptions, that the systems we're dealing with are causal. Okay? Last lecture I said the next set of systems, family of systems we're going to look at are causal systems governed by difference equations of that form. Okay? However, you can view the h of n being 0 for n less than 0. So I'm going to put that phrase in quotes, h of n equals 0 when n is less than 0. Either as a consequence of the causality assumption. So that's a kind of a more abstract way of viewing the h of n equals 0 when n less than 0 thing is. Or a consequence of the universe assumption. So because we're assuming h of n is in the universe. It doesn't matter to me how you think of this, but the point is the systems we're dealing with governed by these difference equations, so we're always going to assume they're causal. And for now, when we're analyzing them, just to even get an I/O relationship, a well-defined mapping from inputs equals outputs, so we need to pin things down. That's why the universe assumption. So this is a fine point. Let me put this in parentheses, but it's good. Thank you for raising it. So it's a fine point, not to be sweated about too much. Okay. So here's a question. Oh, before that, notice notice that this h of n we just constructed, this a1 to the n times b0 u of n, that has infinite duration. So note, in this example, the h of n, in this example, has infinite duration. And that is going to be a general property of these systems when you have recursion terms, A terms in the difference equation. So that's going to be true in general when we have in the difference equation are these AK terms, non-zero AK terms. And that's why that's why people say we're dealing with an IIR system here. We're dealing with a system that has an infinite duration impulse response. So hence, terminology IIR system. IIR is just the opposite or whatever of FIR. It's infinite duration impulse response. And fortunately, unlike FIR, there's no way to construe this as an acronym. You're not going to hear people going around saying, well, I'm looking at an EAR system, you know, or like a FIR. There's always the danger of getting laughed out of the room for calling an FIR system a FIR system, but there's no such danger with these IIR systems. All right. Question: in what sense are the systems that we're talking about here linear, and in what sense are they time invariant? Okay, so in what sense are these causal systems governed by difference equating to that form linear and time invariant? Now, you may say, well, obviously they're linear and time invariant. You know, you just got linear stuff going on, and oh, it's got to be time invariant, whatever. But remember what time invariance is about. Time invariance is about if you shift an input signal, then what happens at the output is the same as what would have happened had you just put that input signal in originally and then shifted that. We're going to go through the VW thing again. But the shifting in that case for time invariance could be in either direction, positive or negative. And the set of signals in the universe of signals that are 0 for n less than 0, that's not even shift invariant. If you shift one of those, then you don't necessarily get another one back. So here's the difficulty with time invariance. Is that the universe isn't closed under shifting. And again, I'm using the word universe very specifically. I'm talking the universe of signals that are 0 for n less than 0 isn't closed under shifting. However, yes? Alicia? Correct, yes, it is closed under shifting to the right. It is closed under positive time shifting. So, however, to resolve this issue, good point, what we do is we consider only positive or rightward, if you will, or delays, or whatever you want to call them, shifts in the definition of time invariance. All right, so what we want to do is we want to make sure, to check time invariance for these systems, we want to make sure that the following is true. Whenever we have x of n going into the system and y of n coming out, okay, and we set v of n equal to x of n minus n0 for some positive n0, or at least non-negative, then what comes out of the system when we put v of n in leads to W of n equals y of n minus n0. Okay? Now the crucial point here is that if x of n is a signal in the universe and I shift it to the right by n0 to form v of n, then v of n is also going to be in the universe. Therefore, v of n gives a well-defined signal in the universe response when I put it into the system. So note, x of n in the universe implies v of n equals x of n minus n0 in the universe when n0 is non-negative. So w of n is well defined. All right, so let's check and make sure that our systems are time invariant when you're talking in the definition of time invariant only about rightward shifts. In other words, if we have this and we set v of n equals x of n minus n0, then the w that arises from v is the shifted y. So let's do the check. So check for this. Check for this property. X of n goes into the system and y of n comes out, means that y of n equals the sum from k equals 1 to cap n, ak, y of n minus k, plus the sum from 0 to cap n of bk, x of n minus k. All right. Now, we let n0 be some arbitrary, positive, or at least non-negative time shift. So now we set n0 be equal to 0 be given, and set v of n equal to x of n minus n0. All right? What comes out of the system when I put v of n? The resulting output signal w of n arises from this difference equation. W of n equals sum from k equals 1 to cap n, ak, w of n minus k, plus the sum from k equals 0 to n, bk, v of n minus k. All right? Now, if you plug in what v of n is, and you figure out the values of w one at a time, okay, if you plug in v of n equals x of n minus n0, and you figure out the values of w of n one at a time, starting with n less than 0, and when n is less than 0, w of n is 0 by the universe assumption. So what you'll discover is that W of n is equal to y of n minus n 0. And I don't want to go through that calculation, but it works. Okay? So that's how you check time invariance for these systems. Now, for linearity, it's pretty obvious. It's pretty obvious what's going on there. If you have two signals x of n, and then you have to assume again that they're in the universe, so they give well-defined outputs. Okay? So linearity is pretty clear. When you do the calculation, that is to say, when x1 of n and x2 of n are signals in the universe, and y1 of n and y2 of n are the corresponding outputs, signals, then if I take C1 x1 of n and C2 x2 of n, so when C1 and C2 are constants, the output signal that arises from input signal x of n is equal to C1 x1 of n plus C2 x2 of n is indeed y of n equals C1 y1 of n plus C2 y2 of n. In other words, if you take a linear combo of input signals and use that as the input to the system, then what comes out of the system is the same linear combo of the outputs that arose from the individual signals that you linearly combined with the input. So same definition of LTI, except we have the universe thing going. Because we need that to ensure that a signal, input signal, gives rise to a well-defined output. All right, so this, I just want to, I'm just giving you this to clear my conscience, this linear and time invariant stuff, because we're not going to be, dealing with any systems of this kind that are nonlinear or whatever, or time varying. I just wanted you to see that if you, even though we're restricting the set of signals we're considering in this context to those in the universe, that there is a way of thinking about linearity and time invariance in this context, and the systems we're dealing with have those properties. All right. Anyhow, I showed you how to find the impulse response of one of these and did an example of it. And you may wonder, does the impulse response for these systems play the same kind of dual role that it does for FIR systems? Remember what the dual role of impulse response is? You can think of it either as the response to an impulse, or what you convolve with inputs to give you outputs. And it turns out the answer is yes. And you can show this mathematically, and I'm not going to do that. So it turns out, as for causal FIR systems, we have, for one of these, a causal system governed by a difference equation with impulse response h of n, that y of n, the output of the system, is always going to be the convolution of h of n with whatever the input signal is. so long as the input signal is in the universe, and we're going to be able to extend that later on. So for all input signals x of n, at least those in the universe. Okay, so again, let me draw the picture. You know, this is something, there's some folks in the class who invariably get sick of seeing this picture over and over and over again, but it's so important. I sort of can't help giving it to you multiple times. So once again, we have this. Delta goes in, h of n comes out, and arbitrary x of n goes in, at least x of n in the universe, and inside the system it gets convolved with h of n, which you can think of as being wired or coded into the system, and what comes out is y of n equals h of n convolved with x of n. At least for x of n in the universe. All right? All right. Now, there is a comment I want to make here about how the convolution of two signals in the universe simplifies a little bit by virtue of the signals being in the universe. Okay, so note that convolution simplifies at least a little bit. And actually, you might not even think of this as being a simplification when you see it, because it's going to give you a piecewise expression. But it is actually simpler because it reduces all ostensibly infinite sums to finite sums. So convolution simplifies a bit because h of n and x of n are both in the universe. All right, so how does that happen? Y of n equals h of n convolved with x of n. And that's the sum from k equals minus infinity to infinity, h of k, x of n minus k. Right? That's the definition of convolution. Now, how does this simplify? Well, and by the way, well, you'll see in a moment. H is in the universe. So what does that mean? That means, before I put what it means, I'm going to say this is because h of n is in the universe, which means that h of k equals 0 for k less than 0 by universe. Because that's true, because h of k is 0 for k less than 0, all the negative k terms in the sum go away. And you're left with the sum from 0 to infinity of h of k, x of n minus k. Okay? So far, so good? Yes. All right. Universe assumption tells me h of anything negative is 0, right? So all the terms in the sum involving negative values of k are 0, which is the same as saying that the limits of the sum are really, quote unquote, really only from k equals 0 to infinity. Get that? It takes some getting used to, but you know, it'll sink in. It'll sink in. All right. So now we've used the fact that H is in the universe. Now we want to use the fact that X is in the universe. So because X, and this is the hard part. This is the hard part of this argument. So what does this go on to equal? Well, it's going to be a two-part thing. All right? And this is going to be when n is less than 0. And this one's going to be when n is bigger than or equal to 0. Okay. The easier one is when n is bigger than or equal to 0, so let's think of that one first. When n is bigger than or equal to 0, the x of n minus k term goes away. It turns off when k passes n, right? Because when k, the index of summation, goes 1, 2, 3, 4, 5, 6, 7, up to n, you're going to have x of something non-negative. But as soon as k gets bigger than n, you have x of something negative. X of anything negative is 0 because of the universe thing. X has to be 0 for negative values of its arguments. So the conclusion is that when n is bigger than or equal to 0, this sum really only goes up to k equals n. So I have this, the sum from k equals 0 to n, h of k, x of n minus k, when n is bigger than or equal to 0. What about when n is less than 0? When n is less than 0, x of n minus k is x of something negative for all k's over the range of summation 0 to infinity. Therefore, it's 0. So every term in that sum is 0 when n is less than 0. You get 0. All right, bottom line. When both h of n and x of n are in universe, y of n equals h of n involved with x of n equals this thing for n bigger than or equal to 0 and 0 for n less than 0, and I can write that as follows. K equals 0 to n, h of k, x of n minus k, all that times u of n. That's a slick way of writing this piecewise way of writing y of n. So that's what I meant by the convolution simplifying a little bit when h of n and x of n are both in the universe. And now you can probably understand why some of you might, why I said that. Some of you might not view this as simpler. You might say, oh, well, this to me is a really straightforward formula, whereas this is complicated. But why is it simpler? It's simpler because everything you're dealing with is finite. You don't have to worry about anything converging, okay? Like infinite sums, whatever. And that's why it's easier. Okay, so now we understand in what sense these systems are linear and time invariant, what sense they give rise to well-defined I/O mappings. The fact that, again, you have impulse response is not only the response to an impulse, but also what you convolve with inputs to give you outputs, at least when the inputs are in the universe. So now we want to talk about, given such a system that's harder than the one we looked at earlier, how do you find the impulse response? How do you find the output corresponding to various inputs? So that's the problem to which we now turn. And we've only seen like a kind of tedious one time after another ways of figuring out the answers to those kind of questions so far. So what we need is a tool that makes it cleaner and faster. And that's what we're going to develop next. Okay, so now what we're going to do is we're going to turn to the problem of, say, finding h of n for one of these systems. In a slicker way than just finding it one n at a time. So that is to say, not quote unquote one n at a time, as we did for our example. And more generally, we're going to turn to finding outputs y of n given input signals x of n. So, and more generally, to finding y of n given x of n in a slick way. Okay, so how do we do that? How do we do that? You could do the second thing in a half-slick way by first finding h of n in a slick way and then convolving h of n with x of n, but you can do even better than that. All right, so the necessary tool, and maybe it's not unnecessary, maybe it's not necessary, maybe it's just sufficient. Well, useful tool, how about that? Is the z transform, so z transforms. All right. So that's what we're going to turn to for the next, like, hour-ish or lecture length-ish amount of time. We're going to talk about z transforms. Now, as I mentioned when we started this topic of these difference equation governed systems, I said that it seems like we're skipping a whole chapter in the book, right? The chapter where they introduce z transforms for the first time. The reason we're skipping that chapter is, in my opinion, all the results in that chapter about z transforms in the special context of FIR systems are trivial consequences of the general theory that covers these more general systems, the ones causal systems governed by difference equations with recursion terms. So, in my view, it's best to learn the more general approach and then go back and read that chapter and see how it specializes in the case of causal FIR systems. So let me just comment before we move on into z transforms. The book introduces these first in the context of causal FIR systems and finite duration signals, and then kind of extends it in a casual way to the infinite duration case. So in the case of causal FIR systems and finite duration signals, and in my view, that the results in this context are trivial consequences of general theory, so that's why I want to move right on to that. So, in my opinion, it's not a good use of time to go that route. And this is an interesting word, route, you know, how, like, when I'm talking about like a computer network or something and sending a message through the network, I talk about routing it. But when I'm talking about like Interstate 81, I'll say Route 81, right? I don't say Route 81. Do people say Route 81? You do? No offense, totally. I mean, yeah, you're allowed to say whatever you want to say, but I always thought that was kind of weird. You would never talk about routing a message through the internet, would you? You would only ever talk about routing. Anyway, not good use. Go that route. Instead, what we're going to do is going to go for the jugular. So, go for the general case, let's say. All right. So what is the Z transform, and how does it come into play? And so this is we're gonna step aside from systems for a little while and talk about a math object. All right. So given a signal x of n, its Z transform. And by the way, in Europe and in some European countries and Canada and Australia, they would call it the Z transform, but we're going to say Z transform here. Its Z transform is given by the following expression. Capital X of Z equals the sum from n equals minus infinity to infinity of x of n, z to the minus n, where, I'm giving you the casual definition first, I'm going to get a little more precise, where z is a complex variable. Okay. So what does it mean to be given by that? And what does it mean for z to be a complex variable? This is an infinite sum, at least ostensibly. All right. So I want to make a couple of comments. First off, so note that, and so my phone is ringing. Let's see if this is a spam call or it's from LA. Who would that be? Well, I'll reject it for now, and I'll answer the call after class. So note, note that this series may not converge for any value of z. So any z values. In other words, x of n may be so awful that you never get that thing to converge. And in that case, x of n has no z transform. Okay. Second thing, if it does converge for some z values, it's generally not going to converge for all z values. You're only going to have a certain subset of z values for which it converges. So the series converges when it does, when the series converges. It generally converges, and you'll see this play out in gory detail in the examples we talked about. It generally converges only for some z values and not all. And this leads to the concept of region of convergence, which we will encounter as we go along. The ROC concept. So please bear with me. More in a moment. Okay. Now what about when we're dealing only with signals in the universe that we've been talking about today, the universe of signals that are 0 for n less than 0? So note that for x of n in the universe, the z transform expression up there reduces to this, sum from n equals 0 to infinity of x of n, z to the minus n. So it's only a one-sided infinite series instead of a two-sided infinite series. Now, for signals in the universe, it turns out you can still have a situation where this never converges for any value of z. But when it does converge for some z values, it's always going to converge for z values whose magnitudes are bigger than that. And that's going to lead us to regions of convergence that look in a certain way. So we'll go on and see those as we go along. All right, so let me just do some examples and see how the region of convergence idea pops up. Okay, and these are the canonical examples that you'll see everywhere. So here's first a few examples. So a few examples of Z transforms of signals in the universe. All right, how about first off, delta of n? X of n equals delta of n. Let's figure out its Z transform. X of z is equal to the sum from n equals minus infinity to infinity of x of n z to the minus n, and that's going to be delta of n z to the minus n, because that's what x of n is. And that series has only one non-zero term, the term n equals 0 term, because of the delta. And that's going to, so that it's going to be a bunch of zeros, 0 plus 0 plus 1 plus 0 plus 0 plus 0 plus dot dot dot. So that equals 1. And the series converges for all z. Okay? So that's in some sense, the 0th example of a Z transform. What is the next example? How about this one? How about x of n? And I'm not going to go in the general list right now. I'm going to do that next time because we only have a couple minutes left. But let's look at x of n equals u of n. And figure out what its Z transform is. X of z is equal to the sum from n equals minus infinity to infinity of x of n z to the minus n. Unit step, again, is in the universe. Unit step. No, never meant it that way. Okay, so this is the sum from n equals 0 to infinity of 1 times z to the minus n. Okay. Now, there's an infinite series. There's a non-trivial infinite series, right? When does it converge? For what z values does this converge? Well, you need the terms to be decaying, right, in magnitude as z goes to infinity. And when is that going to happen? That's going to happen when the z thing has magnitude bigger than 1, right? So this guy here, it converges only when the magnitude of z inverse is less than 1, which is the same as the magnitude of z itself is bigger than 1. Because then the terms decay geometrically. And when the terms decay geometrically, well, you actually have there, that's a geometric series, right? This is a geometric series. And so it converges to 1. It's the sum from n equals 0 to infinity of thing to the n. What is thing? Thing is z inverse. So it converges to 1 over 1 minus thing. So it's 1 minus z inverse. And this is the way most people like to leave it But I prefer to write it in terms of z's instead of z inverses. So I multiply top and bottom by z, and I get z over z minus 1. And here is the bottom line for this example. And then we'll quit for today. So the bottom line is when x of n is u n, x of z is equal to z over z minus 1. And the region of convergence, if the set of z values for which it converges is going to be 1 less than magnitude of z, less than infinity. And why don't we just write it as z bigger than 1 in magnitude? Okay, so this is the formula. And this is what we call the region of convergence. It's a description of the set of all z values for which the series converges. And in general, what we're going to have is, for any z transform, we're going to have a formula and a region of convergence. And it's going to be simpler because we're dealing with signals in the universe. We'll get to that next time. So, for now, I will sign off. And I hope you guys are doing okay wherever you are. And stuff. And I miss you. I mean, it's like this is like the third nice day in a row in Ithaca, which is like a record for April. But anyway, yeah, it is still April, by the way. Now I will sign off, and that's a multi-step process. So it's that awkward moment when I'm standing here clicking and clicking, trying to, whoops. Get rid of this guy. Here we go. All right. Stop. And then it says, do you really want to stop? And